The indefinite integral of a vector-valued function with respect to the parameter t is the set of antiderivatives of r. So that's equal to the antiderivative plus the constant of integration. So the antiderivatives differ by a constant of integration. Now if we write the vector-valued function in terms of the components, so we have x plus the y component plus the z component, where the components are integrable or can be integrated over the interval ab, then r is also integrable, and we can write the definite integral form of r over the parameter t from a to b as the integral of x over t from a to b being the first component, plus the integral of y over t from a to b where the j unit vector is constant, and plus the integral of the z component from a to b. So we can put these in brackets to show the unit vectors are outside the integral, being constants. So by the fundamental theorem of calculus, the integral of the vector-valued function over t from a to b being the definite integral is equal to the antiderivative r of t evaluated at the endpoints of the interval. So we end up with the antiderivative evaluated at b minus the antiderivative evaluated at a. So essentially, if we differentiate r with respect to t, then we get back the vector-valued function. Projectile motion is a typical application of vector-valued functions. So we look at the ideal motion of a projectile that's launched at some angle theta, being the launch angle, at an initial velocity v0. An ideal motion means the projectile is under the influence of gravity, so there's no air resistance or air drag, and we ignore the rotation of the Earth. So by Newton's second law, the only force acting on a projectile is the force of weight, which is the mass of the projectile by the gravitational acceleration, and that's equal to the mass by the acceleration of the projectile. So if we write this in vector form, we have the force of weight acting in the vertical direction, and this acts in a negative y direction, in the direction of the acceleration. And the acceleration is the rate of change of velocity of the projectile with respect to time, and the masses cancel, so we get minus the gravitational acceleration in the vertical direction. So this is a differential equation, and we have our initial condition that the position of the projectile at time 0 is denoted r0, and the initial velocity of the projectile at time 0 is the launch velocity, being v0. So if we separate the variables and integrate both sides of this equation, so we integrate from the initial velocity to the current velocity at time t, and we take our reference time of 0 and we integrate to the current time t. So that gives v minus v naught, which we'll take to the other side of the equation, and minus g by time t, and the unit vector j is constant. And similarly, the velocity is the rate of change of position with respect to time. So if we separate the variables and integrate both sides of this equation, from the initial position to the current position at time 0 to time t. So we get r minus r naught, where we'll take r naught to the right hand side of the equation, and we have plus v naught t minus the gravitational acceleration by the time squared on 2 in the j direction, being the y direction. Now we can write r naught in component form. So I have the x component plus the y component, and r naught's a zero vector if we take the origin at the initial position of the projectile, but in the general case r naught will not be zero. And the initial velocity can be split up into components. So we have the horizontal component being the speed or the magnitude of the initial velocity by cosine of the angle theta in the I direction, plus the speed by sine theta in the j direction, which gives this vertical component. And now we can write the position vector, which is a function of time, in component form. So we have the initial position in the x direction plus the initial velocity in the x direction multiplied by time t in the horizontal direction plus the y component. So that would be y naught plus the vertical component of the velocity, which is v naught sine theta by time t in the y direction minus a gravitational acceleration by time t squared on 2. So this is the component of the position in the vertical direction. So if you differentiate this, you get the velocity, which gives v naught cosine theta in the x direction plus v naught sine theta minus the gravitational acceleration by time in the vertical direction. And if you differentiate again, you get the acceleration. So all these terms are constant and they'll drop out, except the gravitational acceleration term in the y direction. So essentially, this here is the x component of the position, and this here is the y component. So x gives the range of the projectile, and y gives the height of the projectile, which depend on the initial speed of the projectile and the launch angle, which give the velocity. Given our general vector-valued function for ideal projectile motion, which we derived, we can derive a few quantities, being the maximum height of the projectile, the time of flight, or the time that the projectile is in the air, and also the range of the projectile. So if we differentiate this equation with respect to time, we get the velocity, which is v naught cosine theta in the x direction plus v naught sine theta minus the gravitational acceleration by time in the y direction. So the velocity of the projectile is constant in the x direction. So the x component does not change length, but the y component of the velocity at the top of the trajectory is 0. So therefore we set this y component to 0. So we have v naught sine theta minus gt is equal to 0. And this will give us half the time that the projectile is in the air. So we get t is v naught by sine theta on g. And therefore the total time that the projectile is in the air is twice this time. So we got the time of flight. And now to get the maximum height of the projectile, being y max, we substitute half the time of flight into the y component of the position. So that gives y max is equal to y naught, which we'll ignore because we'll take the origin at the launch position of the projectile. So we have v naught sine theta by half the time of flight. So that will give v naught squared sine squared theta on the gravitational acceleration minus g on 2 by t squared. So we have v naught squared sine squared theta on g squared. So if we cancel out one of these g's, then we get y max is v naught squared sine squared theta on g by 1 minus a half. So that gives v naught squared sine squared theta on 2g. And to find the range of the projectile, we can substitute the total time of flight into the x component of the position. So we have x, and we'll ignore x naught, where we're taking the origin at the launch position of the projectile. So we have v naught cosine theta by the time of flight, which is 2 by v naught sine theta on the gravitational acceleration. And 2 cosine theta sine theta by the trig identity can be written as sine 2 theta. And this is the range of the projectile. Now let's make some room over here, and we can show that the path of the projectile is parabolic by taking the x component, and we'll take x naught as 0, where the launch position is at the origin of the projectile. So we have v naught cosine theta by time t, and solving for time t, we get x on v naught cosine theta and therefore the y component is equal to y naught, which will again take as 0. So we have v naught sine theta by time t, which is x on v naught cosine theta, and minus g on 2 by t squared, which is x squared on v naught squared cosine squared theta. So if we simplify this, we get tan theta by x minus g on 2 v naught squared cosine squared theta by x squared. So we have y as a function of x. And therefore we can say that the path of the projectile is parabolic given this x squared term. Let's integrate the following vector valued function. So we can integrate this by integrating each component. So what we get is t squared on 2 plus cosine t plus a constant of integration. So that gives the I component, and plus t minus sine t plus another constant of integration. So that's the j component, and plus 3t squared on 2 plus another constant of integration. So that's the k component. Given the acceleration of a particle and initial conditions, find the position of the particle as a function of time. We'll recall that the acceleration was the rate of change of velocity with respect to time, and if we separate the variables and integrate both sides, we have an integral from the initial velocity to the current velocity at time t on the left hand side, and on the right hand side we integrate with respect to time. So we can separate this into an integral from time 0 to time t, and we integrate the x component with respect to time while taking the constant unit vector outside the integral. And next we have the integral from time 0 to t of minus sine t with respect to t, taking the unit vector outside the integral, and then we integrate t over time from t0 to time t, and multiply this by the constant unit vector k. So on the left hand side we have v minus the initial velocity, which is 1 in a j direction, and we can take this to the other side of the equation, and we can take the minus outside the integral and integrate cosine t, which becomes sine t from t equals 0 to time t, and multiply this by the unit vector I, and then we have the integral of minus sine t, which gives minus minus cosine t, evaluated at t equals 0 and t, multiplied by the unit vector j, and finally we have the integral of t, which gives t squared on 2, evaluated at 0 and t, multiplied by k. So that's equal to j minus sine t in the I direction, and plus cosine t minus cosine 0, which is 1, in the j direction, and plus t squared on 2 in the k direction. So as we can see, plus j minus j cancels out this term, and this here is our velocity. And if we set this equal to dr dt and separate the variables and integrate both sides, While recalling our initial condition that was given in the problem, where the initial position is at x equals 2, y equals 0, and z equals 0. So that gives r of t minus the initial position, which we'll take to the other side. So that would give 2i. And then integrating each of these expressions, we get minus cosine t evaluated at t and 0 in the I direction, plus sine t in the j direction, plus t cubed on 6 in the k direction. And simplifying this, we get 2 minus 1, which is 1. Then we have plus cosine t in the I direction, plus sine t in the j direction, plus t cubed on 6 in the k direction. And this is our position as a function of time. So as we can see, if we substitute t equals 0, we get an initial position of 2, 0, and 0. And recall the initial velocity was 1 unit in the vertical direction. So if we substitute t equals 0 for the velocity, we have 0, 1, and 0. A projectile is launched at an initial speed of 30 meters per second and an angle of 45 degrees. Find the position and velocity of the projectile when 5 seconds have elapsed, and we'll use the following gravitational acceleration of 10 meters per second squared. So recall that the position, being a vector valued function, is the initial position in the x direction plus the initial speed by the cosine of the launch angle by time t in the I direction plus the initial y position plus the initial speed by sine theta by time t minus the gravitational acceleration by t squared on 2 in the y direction. So if we take the origin to be at the position of the projectile, we can get rid of these terms, and substituting for v0 being 30 meters per second, the launch angle of 45 degrees, a gravitational acceleration of 10 meters per second squared, and an elapsed time of 5 seconds. And calculating this out, we get 106 meters in the x direction and minus 18.9 meters in the y direction. So that means that the projectile was not launched from the ground. So it'll land at a position of 19 meters below its launch position. Now the velocity can be obtained by differentiating the position with respect to time. So that gives v0 cosine theta in the horizontal direction plus v0 sine theta minus g by time t in the vertical direction. So if we make the same substitutions, we get a velocity of 21.2 meters per second in the I direction and minus 28.8 meters per second in the vertical direction. So the position is in meters, and the velocity is in meters per second. And therefore the velocity, after 5 seconds, is acting downwards and to the right, if we resolve it in those two components. So the projectile is descending at 5 seconds.